Okay, it's week 10, just a few days left. So today I'll cover some stuff, more on Bootstrap, okay? Today will be the last day of content on which you will be tested in the final exam, okay? So then, still come to class on Wednesday and Friday, but Wednesday and Friday stuff I think is interesting, but will not be, you won't be tested on that per se, okay? I have uploaded or I posted a homework 6, but you'll notice that's in quotes. Okay, so what that means is there's a homework assignment, but I'm not going to grade it. Okay, so you got to submit something or whatever. Okay, but then when it comes time to grading, we're not gonna read through it. We'll just give you credit for homework 6, okay? So you're welcome. So I know week 10 is always stressful and stuff, so I don't want to add to that. But I did want to post a homework because it's my intention. All of these homework assignments I post, it's my intention that they help you learn, right? And so you are responsible for learning randomization tests and Bootstrap, and so there is a homework assignment that kind of walks you through some of this stuff, and so that it's intended to help you in your preparation for the final exam. But if things get too crazy in your other courses, you don't have to worry about homework 6 actually being graded there. Okay, so but please still work through it and learn the content there. Okay, are there any questions about that? What's that?
I like how it's in quotes.
Yeah, it's in quotes, homework 6, right? We put, that's how air quotes work. So it's more like free points is what it should be, okay? Free points in the place of homework 6, but learning opportunity, I don't know, whatever you want to call it. Okay, today we'll cover more Bootstrap stuff, okay? And specifically we'll look at some of R's built-in tools for Bootstrap and how that can be used. And then we'll do that. And then, Wednesday and Friday we'll talk about some other stuff. We'll talk about the final exam and whatever. Okay. All right. Well, so actually, I have this is kind of the content of homework 6 that I've got up here, and I guess I'll just kind of walk through parts of it, and then you can kind of explore it on your own. Also, in the assignment, I've linked a couple articles. One is to this article on 538, which is I think it's a fun website. You guys know about 538? There's a guy, Nate Silver. He back in 2008, he ran. He had this little blog called 538, and it correctly predicted the Electoral College, every single seat in 2008, and this launched him to fame. And he did very well in the 2012 election. And as far as the 2016 election, everybody got that wrong. But he was, his blog basically said he gave Hillary Clinton a 70% chance of a win, whereas other people were all 99.9% chance of win. And so anyway, so he's well known. He got bought by ESPN because he actually started off doing baseball statistics. But anyway, there's an article here just about science and how it's not broken, because lately science, the whole idea of research articles has come under fire largely in part to the use of p-values, okay? And so, we use, like, in your intro stats class, it's like the biggest thing that we focus on is getting you to understand what a p-value is. And in a lot of disciplines and a lot of different sciences, a lot of the research is done with kind of an intro statistics level of understanding of the statistics portion, okay? They have PhD understandings of their related discipline, but when it comes to the statistics part, a lot of disciplines or a lot of people are still kind of working at this fairly intro level of statistics. And because of that, and we put so much emphasis on p-values at the intro level, there's probably an overemphasis on p-values in these different science disciplines. And so because of that, it's come under a lot of fire. And, I'm a statistician, and so, I love p-values, but I also know that, probably the way we use p-values is problematic. When statistics was being kind of founded, we never intended for p-values to be the be-all, end-all way to make decisions. And it was always kind of a little bit more of a nuanced view. You get a certain value, and it gives you an idea of how much confidence you can kind of put in to your hypotheses. But now a lot of journals just say, if it's over 0.05, we're not going to publish it, and only if it's under 0.05. And so you get a lot of, anytime you draw an arbitrary line, weird things happen right along the border of the line. And so so that's kind of what's happening. And so this talks about the idea of p-hacking. The American Statistical Association released a statement on p-values last year, basically saying p-values are good and useful, but the way we use them is problematic. There's a group of prominent statisticians that are kind of pushing for p-value, the significance level to be 0.005, so 1/10 of what it used to be, before we say something is significant. So, who knows what will happen. But anyway, I think these are good articles to read through. And but we'll take a look at Bootstrap today, and so we looked at parametric and non-parametric bootstraps. And so here you got to load up packages Bootstrap and Boot, and we'll take a look at this one data set that exists in library Bootstrap. Okay. And okay, so let's go back. So we'll do library Bootstrap, and we'll look up. We'll clear everything out of our environment. Okay, so inside library Bootstrap, we have this data set called Law 82. And if we ask for what Law 82 is, we are going to pretend that in the USA, there are 82 law schools, and this represents the universe, the entire population of all law schools in the United States. There's more than 82 law schools in the US, but as far as our data set, we're going to pretend that this is all the law schools ever. And when we look at the data set there, the two columns of interest to us are the columns Lsat and GPA. So there's, if you want to go to law school, you have to take the Lsat, and this is like the test to see, how well prepared you are, and a lot of schools have kind of cutoffs based on your Lsat score. And here we just want to know, is there a relationship between between a school's Lsat and their kind of GPA? So So we can do this and we'll create a plot of this. Let me just copy this thing actually. What did I do? Law 82. Law 82. Okay, so this is everybody. Okay, so this is the plot showing the relationship between Lsat and GPA, and we can see there's a positive relationship. And if we calculate the correlation between Lsat and GPA for all 82 schools, we get a correlation around 0.76. Okay. There's also a data set or a matrix called law, and this one has 15 values, okay, or 15 rows. And this law represents, of the 82, we randomly selected 15 of these schools. Okay? And so this is akin to, you know, when you have a random sample, you only get to see your sample, and you got to make conclusions based on your sample. So we're going to say we have our 15 schools here, and we'll plot. We'll just take a look here, and we'll create a plot of this. So I'm using, inside my command, I'm using the range of our original data set so that everything is put on the same scale. So if I plot this, these are the 15 out of these are the original all 82, and then here's just 15 randomly selected schools. Okay, and then we can calculate what's the correlation between Lsat and GPA for those 15. So for all 82, the correlation is 0.76. For the 15 randomly chosen ones, we get a correlation of 0.776. Okay. That's just for these 15. If I randomly select another 15 schools, okay? So here I'll do set seed 1, and I'm going to subset law 82. I'm going to just take the second and third columns, but which rows I'm going to take is I'm going to just select 15 at random from the numbers 1 through 82. Okay, and I'm going to call this law sample 1. So here is law sample 1, and I will plot law sample 1. And let me just kind of plot this against the original data set. So here's everybody, and then here is my random sample of 15. Okay, and we can see this is one random sample of 15, and here's a different random sample of 15. And we can see these two things look very different, even though we can see that it is just, it's not like I'm making up new data points, it's just a random selection from, this is everybody, and this is just my 15 that I've randomly selected. You know, I should just do points. So this is everyone here. Let me just add a few lines here. Everybody. Points. And we'll do color equals red. PCH. Right here, there's 19. Okay, so this is everybody. Whoops. 82, 82. Okay, so this is everybody. And then here's the 15 that we've randomly selected. If I do this again, we'll do law sample 2, and we'll use green. So here's just another 15 randomly selected. So this is all 82, and I've selected the 15, and you can see there we have just the 15 of interest here. Okay, and so we can see that depending on which ones we do, we get different points out of our 82. And here we'll just do this one more just to kind of illustrate really what's happening here. We'll do blue. We'll do loss sample 10. Okay, so I got this one and this one. Let me just delete this. Oh, shoot. Okay, here's the red. Here's the green. Here's blue. Okay, so depending on which ones we select, our estimates of the correlation can vary quite a bit, right? So when you look at the blue dots, it seems like the correlation is going to be quite high, and indeed that's the case. The correlation of these blue dots is 0.8177. If we look at the green ones, the correlation there is 0.627, and if I look at the red ones, the correlation is even lower at 0.27. Okay, so depending on which set out of the original we're looking at, the correlation that we calculate could vary quite a bit. And when we do Bootstrap, it's gonna just, we don't get to see all the entire universe. We only get to see just the random sample that we have, and we're saying, you know what, because it was selected randomly, I'm just going to duplicate these blue dots over and over and over again, and that's going to be my stand-in for what the actual population is. And so so that's what we have here. Okay, and so we'll do Bootstrap, and so with Bootstrap here, I'll do 500 replications on our sample law. So law, we've got 15. And so what I'm going to do is, because I've got a data set here, I'm going to just subset the data set of 15 using 15 randomly selected values with replacement. So I'm going to do sample 1 through 15. Effectively what I'm doing here is I'm going to do sample 1 through 15. I want 15 of these, and I'm going to do replace equals true. Okay, so here, these are the values 1 through 15 sampled with replacement, and I get 7, 1, 4, 6, 13, 13, 10, etc., etc. Okay, and here I'm going to then subset this column Lsat. I'm going to say law $Lsat, and I just want the ones corresponding to the index. So I want row 7, what is it, 7, 1, and 4, so I'm going to call 555, 576, 578, so on and so forth. And so if I subset using, oh, I didn't save this. So this time, what is my index? Okay, my index are 923. So I'm going to take row 9, 651, 635, and so on, okay? And then we subset the values that way. So I get LSAT, I get 15 values selected with replacement. I get GPA, 15 values selected with replacement. And then we're going to calculate the correlation between these two. Okay, and we will save this into results. And so I'm going to have a vector results here. And that's it. Okay, so this is Bootstrap. Again, all I'm doing is I'm just resampling my data with replacement. So sampling with replacement is effectively making an infinite number of copies of it and drawing a sample. And so because our original sample is of size 15, when we sample with replacement, we're taking random samples of size 15. So we sample with replacement, we get all of this, and it works out. Okay, so that's what we have. So we select which rows we want using to get index. This is going to be our vector of 1 through 15, and then we calculate the correlation there. All right. So this is kind of doing Bootstrap our manual way. Is this loop okay? Does that make sense to everybody? This is our non-parametric Bootstrap. We're resampling our data with replacement. Okay. And then if we want to calculate get an estimate of our standard error, we just take a standard error of all the different results we had. Okay, so we just say standard deviation of our results. We get 0.135. Okay, standard error of our estimated standard error of our results there. Okay, if we want to use library boot, so this is a totally legit way to do Bootstrap. Is just kind of write up the loop yourself and sample with replacement. R comes with the function boot, and it performs Bootstrap. And some of the nice features of boot, so it runs, and then you have functions like give me a Bootstrap confidence interval, and it comes with other features that are a little bit more work to do manually. And so sometimes it's nice to use library boot. If you want to use library boot, the way that works is we just call the function boot, is that the function takes on the arguments data and statistic and the number of replicates. Okay, everything else comes with default values, and so really we only have to provide it with 3 arguments. Everything else does come with default arguments, and so you don't have to worry about it. I mean, you can change them, but you just need the data, the statistic, and R, the number of replicates. So the data is straightforward. That's just going to be the sample that you have, and R is how many replicates you want. So usually like what, 500 or 1,000 or a few thousand, something like that. The statistic, this is a function that we apply to the data and returns the value of interest. So in our case, what we're going to do is we're going to apply the function statistic to our law school sample. So our data is going to be law, where it has 15 rows in it, and we're going to apply the function to calculate the correlation between Lsat and GPA. So what we have to do is we have to write a function that will calculate the correlation between Lsat and GPA. The function for statistic always takes in 2 arguments, the data and the index. So this is the hardest part about using the boot function, is that you have to write a function that calculates your statistics. And that function always takes the arguments data and index, and basically what it does is first what you want to do is you want to subset your data according to the indices. All right, in our case, we've got 15 rows. Boot is basically going to do this part for us. It's going to provide an index, which is going to be 15 rows randomly sampled. And then so we subset our data using that. Once we've subset our data, we extract the Lsat column, extract the GPA column, and calculate the correlation between those 2 things. Okay. And so this function here effectively does the same thing that we've done here. Okay. Inside our manual Bootstrap, we randomly sample rows, values 1 through 15 to tell us which rows we want, and then we extract those values from Lsat and GPA, and we calculate the correlation between those 2. Here we do the same thing. We write a function of 2 arguments, data and index. We subset our data using the indices, and then we extract the Lsat column, the GPA column, and we calculate the correlation between the 2. Okay. So I have that written here. You can write the same function just a tiny bit more concisely so that you don't have to write all of these things. And you can just say subset the data using the indices, take the first column, subset the data using the indices, taking the second column, and return the correlation. So both of these two functions work exactly the same way. Okay, once we have that, then we just run the boot function. Okay, so boot, we do boot, we give it the data set, in our case our sample law, 15 rows. We give it the function that we just wrote up, and we say we want to do this 500 times. Okay, here, let me call this results, boot results, or we'll just call this B results, just as. Okay, so I've got the results there, and then if we look at what the results of Bootstrap is just a large list. Okay, I mean not large, but it's a pretty big one, and so here we get the first thing it returns. T0 is just if you applied the function, correlation function, to the data itself, okay, to the 15 law schools without any kind of resampling. And then here, these are what happens if you apply the function to different Bootstrap samples. So again, the first time we sampled 15 with replacement, and we applied the function, we got 0.6709. We ran it a second time, and we get something different, and so we get just different values of our Bootstrap. Okay, we did this 500 times, so we get 500 values. It also includes the original data itself. It includes seeds, which I'm not entirely sure what that does. Here's how the function is being calculated, and then it says it's ordinary Bootstrap, and it has all of this other information. Okay, if we just want to get a standard error estimate, we just take the standard deviation of all of our Bootstrap results. So I just say standard deviation results $T, and the standard deviation or standard error estimate is going to be 0.1335. So that's using library boot. We might ask, how does our estimate of the standard error itself, how does that depend on the random sample that we have? So we have a random sample of 15. If somebody else also randomly sampled 15 schools from the population, and they did a Bootstrap, how would their standard error estimate differ from ours? Okay, and the answer is it varies, maybe surprisingly a lot. Okay, so here I'm going to just run the same function, boot, using the correlation function on 500, but this time I'm doing a different random sample. So here I've got just another random sample of 15 rows. We call that law sample 1. And we'll do this, and we'll say, okay, so when I did Bootstrap on this other sample, I got a standard error estimate of 0.2166. Here's another random sample of 15. I get a Bootstrap estimate of 0.152. And over here, I have another random sample, and here I get a Bootstrap standard error estimate of 0.054. Okay, and so we see our standard error estimates vary quite a bit based on the original sample that we have. Okay, and so what I want to do here is what I'm going to call a meta study. So we're going one level higher, and we're going to say, what if I have access to the population, and then I try out taking a random sample of 15, and then pretending that's my sample, and then doing Bootstrap. And then I'll go back to the population, take another random sample of 15, pretend that's my sample, and then do Bootstrap. And I'm going to do this 1,000 times. So this is going to take a little while to run, just because I'm doing 1,000 replications, where every single time I'm randomly sampling the population, taking a new sample of 15. I'm going to pretend that that's the sample I have and perform 500 Bootstrap replications. So every time we do Bootstrap, it takes a little bit of time, and then we're going to do that 1,000 times. And every single time we do that, we're going to calculate the standard deviation of our Bootstrap results, getting a standard error estimate. So I'm going to get 1,000 different estimates of this, and I run this. So it's going to take a little bit of time here. Every single time, it's going to the population, randomly sampling 15 values. After randomly sampling 15 values, it does Bootstrap on those 15 values to estimate the standard error. And we just want to see how much do our standard error estimates differ based on the different random samples that we got. Okay, it's still running. Okay, oh, all right, I was getting nervous. Okay, so when we look at our standard error estimates, they vary as slow as 0.03 to as high as 0.4. And then here is a kind of a density plot of our different standard error estimates. And so we see, most of the time we're around here, but sometimes it's way higher, sometimes it's way lower. And so it kind of makes sense, but it also it serves as a warning that when we do Bootstrap, the big assumption that we're making is that the random sample that we have is representative of the population, and therefore we can just make infinite duplicates of that sample to be a stand-in for the population. But we see that if our random sample is not a great representation of the population, our estimates based on that could be quite a bit off, okay? And of course, when you have your random sample, you don't know if it's a representative or not, and you're just kind of hoping that it is, and in the long run, Bootstrap should get it right because random sampling should be representative in the long run. But of course, for any one given day or one given random sample, it may or may not be representative. Okay. In the homework, I have a few more exercises for you to kind of work through and try out, and I also fully write out the code for the randomization tests. And so you are responsible for learning Bootstrap and randomization tests for the final exam. So I definitely encourage you to work through the homework assignment. I want to work through a few examples of maybe writing a few more functions for library boot, just because that's probably the hardest part to do. Okay, so here is maybe I'll post this code also, right? Like let's say we want to do to use Bootstrap to estimate the standard error of the mean. Okay, and so here we will start with a population here. My population is going to have 300 individuals sampled from a normal distribution, and this normal distribution has a mean of 100 and a standard deviation of 15, and we're going to round it off to 0 places after the decimal. And so this is effectively kind of what IQ scores, if we believe in IQ scores, what this should look like. IQ scores are designed to have a mean of 100 and a standard deviation of 15 or 16, depending on whose IQ test you are taking. And so if we take a look at our population, this is what it looks like. We can ask, what is the mean of our population? Oops, if I can spell. So the mean is 99.2, and the standard deviation of our population is 14.969. And if I create a histogram of our population, it looks kind of like this, okay? So it's supposed to look normal. It's got, maybe it looks a little bit off, but our population only has 300 people in it. What I'm going to do now is we're going to take a random sample of 15 values out of the population. So I just do sample population, 30 values from the population, okay? And so, again, the mean of the population is 99.2. I'm taking a random sample of 30, and these are the 30 values that I have. And so the mean of my 30 values is 96.53. So I take 30 values at random. And we want to do Bootstrap to get an estimate of kind of the standard error based on this, right? So if I create a histogram of just our random sample, these are the 30 values that I've randomly sampled. What we want to do is we want to do Bootstrap. So basically, I'm going to take these 30 values and I'm going to randomly sample 30 values with replacement from this pool of 30 values. Okay, that's going to be my Bootstrap sample. And so if I want to use library boot, I've got to provide it a function to calculate the mean of my Bootstrap sample. And so to get my Bootstrap sample, first I will take so the function is a function of always two things, data and the index. And so the data that we provided in boot is just a vector of 30 values. So if I subset my data using the indices, all I do is just do data square bracket index. Okay? So because index is always going to just be, it's just going to sample, in our case, 30 values with replacement. All right, so it's just going to say we want to take value 15 and value 7, and so it's going to come over here and it's going to take, I think the 15th is 90, and then the 7th value, 1, 2, 3, 4, 5, 6, 7, is going to be 111. So if I subset data using these index, yeah, it's going to take the 90th, and then 111, and then the 19th, which is going to be 104, and so on and so forth. So it's just sampling this with replacement. So the function that we're going to do is going to be data index. This subsets our data. This creates our Bootstrap sample. And then we just want to calculate what's the mean of this. And that's it. That's about as simple of a function as we can write as far as doing some Bootstrap estimation here. So we just say this is the mean function, and then we want to do bootstrapping here. So let me just, and then so we do that. This is going to give us our results. And if we want the standard error estimate, I just do $$T, and the standard error estimate is 2.507. Okay, what would be the true real life standard error estimate? It would be 15, right? 15 divided by the square root of 30, right? So s over the square root of n, or sigma over the square root of n. And so the real life standard error estimate is 2.738. Our bootstrapped standard error estimate's a little bit smaller than that. But that's what we have here. Okay. Are there questions on this? Using Bootstrap to get kind of a standard error estimate for the mean? Okay. We can use Bootstrap to conduct hypothesis tests, right? So we did this on Friday. Briefly, we were looking at education achievement of Latino immigrants, and we did some bootstrapping there. Okay, we can use R's boot function in a similar fashion too. Okay, so here I'm going to just set up two groups here, and we'll do here I've got group 1. I'm going to take 20 random values drawn from the normal distribution with a mean of 100 and a standard deviation of 15. And we got group 2, 20 random values drawn from with a mean of 105 and standard deviation 15. Okay, and I'm going to just kind of pull these together into our data set. And if I take the mean of the first 20 values, that's the mean of group 1. So the mean of the first 20 values is 99.05. Did I do this right? Okay. And then the mean of the second 20, is that right? Ends up being lower. That's strange. Let me try this again. Yeah, here, let's just change our seed here. I don't know what's going on. That's fine. Okay. Well, we're just taking random values, and we're getting something different. Well, if I use the original seed, the mean of the first group is 99.05 and the mean of the second group is 93.6. We would have expected the mean of the second group to be higher, but that just didn't happen here. But anyway, what we want to know is how would our data be evidence that that the two respective populations have different means? Okay. And in our case, the original populations should have a mean of 100 and 105. When we look at our data, we're getting means that are, quite different from that. But can we still detect a difference between our two original populations? Okay, and so the mean of group 1 in our case is 99.05. The mean of group 2 is 93.6. And so our observed difference is about 5.45 points here. And what we want to do is we want to do Bootstrap on our data here. Okay? If the null hypothesis is true, we can just throw all 40 values into the same thing and say this is coming from one population. We can treat all 40 values as one population, and it doesn't matter if the first 20 are different from the last 20 or whatnot. We're going to just treat them as all from the same population. And so if the null hypothesis is true, we can just take our data. In our case, it's the vector of 40 values, and just mix them up using our bootstrapped indices. So we're just going to say take these 40 values, sample them with replacement. Okay. And then after we've sampled them with replacement, we will just throw the first 20 into one group and the second 20 into another group, and we're going to calculate the difference between the mean of the first 20 and the mean of the second 20. And so here, this will be how different are two means if we just threw all 40 values into one population and then just resampled them and took 20 into one group and 20 into another group. Okay. So this is going to be the function that we run. The difference function is going to calculate the differences that we get, and that's what we use. And here I'm going to just run boot on the data. My data is just a vector of 40 values, where the first 20 are group 1 and the second 20 are group 2. But we're going to apply the difference function where we just pull everything together, shuffle them up, and spit this out. Okay? And then to get our p-value, we want to know how often did our Bootstrap results produce a difference that was greater than the difference that we observed. Okay, so how often did our Bootstrap values produce something as big as the observed difference that we got? And this says this happens about 15% of the time. Okay, so how often, when we just shuffled all 40 values into one pool and then arbitrarily threw 20 into one group and 20 into another group, how often do we get a difference that was 5.45 or greater? That happened about 15% of the time. Okay, and we can see, you know, what would happen if I used if instead of taking 20 values, if I used 60 values, and then I threw in the kind of the first 60 and the last 60, and we did the mean between these two things. And we'll do the same thing here. You know, how often would we get something like this? So here, when I take the mean of the first, I get 96.5 versus 106.15. So I get a difference of, you know, negative 9.6. Here I need absolute value here. Okay, and then so we'll do Bootstrap using this same thing. Throw 60 into one and the other 60 into another. We'll do the Bootstrap there, and this didn't happen at all. Okay, after 1,000 replicates, we can try this with 10,000. Okay, and this happened only 3 times. 3 times out of 10,000 did we get something different. So here, this was something with, you know, when we had 60, random sample of 60, it was quite pronouncedly different. So so who knows? Okay, what's my observed difference this time? Okay, changing just the seed, we might get something a little bit different, but depending on our data. So anyway, you can do Bootstrap using library boot for other types of functions, not just calculating the standard error. But you just have to ask, what is the value that I'm calculating, and what we have there. Okay, we'll end here. I'll clean this code up and I'll post it online as well.